Ladies and gentlemen, please welcome Sanjay Radya.
Hi. Hi, good afternoon, everyone. Thank you for coming. I'm going to talk about HDFS and what is new in this upcoming release and some of our thoughts on what's going to happen in the future. Okay. A little bit about myself. I'm a founder architect at Hortonworks. I was part of the original Hadoop team at Yahoo since 2007, the chief architect of Hadoop Core at Yahoo, and I'm a PMC and a committer, and worked on a number of interesting projects in the past. So I'm going to actually talk about, this is roughly the agenda. I'm going to talk about what's new coming in Hadoop 2.x, Hadoop 2.0. We are just announced that 2.1 beta just got released last night. Okay, so that's a big step forward. I'm going to talk about some of the features there, federation, high availability, snapshots, some of the other features, and then kind of go into futures and kind of break it into kind of two parts, major architectural directions we are thinking of, or partly on the way, and some short-term, long-term features. Okay. So we have been very, very hard at work. There's the write pipeline, append, scalability, performance, a whole bunch of enterprise features, operability improvements, enhancements for other projects in the Hadoop ecosystem. It's actually what is coming out in 2.x is a set of changes that have actually been in works for over 3 years. Because between Hadoop 1 and Hadoop 2, there was a fairly big gap for several non-technical reasons. Okay, so over 2,000 commits, over 1 million lines of changes. Actually, all these changes at about 150 contributors. So this kind of really shows you that open source is working extremely well. In fact, what is also exciting, a lot of new contributors. So we have contributors who have less than 3 patches. So also welcome their changes and for them joining the community. Okay. Over 350 lines of changes just in HDFS and common. Okay, so as we went into Hadoop 2, it turns out we were actually building on a very rock-solid foundation. We had some very important design choices that were made. We relied on storage on the operating system's file system rather than use a row disk, and that was a major part of making Hadoop rock solid, and I'll kind of talk about that. The storage system is completely fault tolerant. It deals with, by using multiple replicas, it deals with node failures, disk failures, and in fact, even corruption occurring on your disk sectors. Okay, so this is completely built into the architecture. It has a NameNode master that is extremely scalable in terms of number of operations it can do. It can support a cluster that is over 4,500 nodes that it's actively bombarding against it. Okay, and it has a reliability. We published a study a couple of years ago, 7 nines of data reliability. We believe it is actually higher than that this year, but we haven't done the studies for me to say that. And this is actually the most important part of Hadoop of storage. If you're building some of the upper layers, like when you're doing compute, you can say, well, I fail 1% of the time or 5% of the time. You can't play that game with storage. I can't come and tell you, you know what, 1% of your data or even 0.5% of your data gets lost. Unacceptable. So storage, you just cannot. You have to be solid. And in fact, even though there's been a lot of talk about NameNode single point of failure, the studies we've done at Yahoo that we've published, we had about 0.58 failures, unplanned failures, or unplanned failures because of hardware or something in 25 clusters. Okay, so it still has a pretty rock solid reliability. Okay, and it is very, very operable. Hadoop is actually very easy to operate. It is not common for some of the big clusters to use one operator per 3,000 nodes. That is unmatched in any other system. Okay, it has very, very fast time to repair on a node or a disk failure. So for example, you can lose a 12 terabyte node, and Hadoop can recover that in minutes to half an hour, depending upon how many nodes you have in your cluster. Compare that to a RAID array. In a RAID array, you lose a 1 terabyte disk, and it takes you 20 hours to recover. Okay, and you know you better fix that thing before the next failure occurs, otherwise you lost your data. Hadoop, you don't blink about it. On a 3,000 node cluster, 12 terabyte node gets replaced in minutes, okay? Literally, I mean, it's just amazing to see that because it all happens in parallel, okay? Scalability, so it's been proven to be scalable at over 100 petabytes per cluster, over 500 million files on a 4,000 node single cluster. I'm not talking about number of bits that can be used to address under 100 petabytes. I'm talking about real deployments, okay? Right now, there are over 60,000 nodes that have deployed HDFS in production use, okay? So what I'm going to talk about now is get into the feature changes, the changes that have made to this rock-solid foundation, okay? One of the things to the operators, my time clock is actually not going down here, so I don't actually have a clue how much time I've used up. If you could please start that. Thanks. So the first big change is actually in the storage layer. And so what we have done is we have kind of innovated where the Hadoop block storage was only usable by HDFS namespace. We have generalized that so that we can actually have multiple name nodes. So the storage layer at the bottom, which I call the storage service, has actually become generalized. And the first use case of that generalization is that you run not one name node, but you can run many, many HDFS independent namespaces. And that helps in scalability, helps also where you have independent customers that want to run or independent tenants that want to run. They want the isolation. Okay. It also means that we can do new things, like, for example, we could build a new name node and run that in parallel with the other one that does, say, partial namespace in memory. In fact, I have an intern student from CMU who's doing exactly that right now. And once that project is finished and you wanted to deploy it, you could deploy it on the same HDFS storage system and run it on the side. So it will allow that sort of innovation very, very easily. We plan to make the temp storage of MapReduce, which doesn't use HDFS, to be used that as an independent block pool. That will be, for example, you could build a block an object store like a key value like S3 directly on the same block storage now because it's now a very simple layer. Shadow file systems, in fact, I was talking to somebody from Amazon, and he wanted to basically say, I want to run a different kind of a file system where I want to cache some of the blocks from S3 that is a lot onto the same storage system, but not into HDFS. So kind of build a caching file system. Much, much easier to do now. Okay. And really what we want to move down towards is the management and the replica management still happens as a library in these high-level services. We want to move that down actually into the blocks and storage system. So this will really make a whole bunch of things. Things like distributed name node will a lot be simpler to also do. Okay. So basically, with federation, what happens is what I've shown here in this picture is two layers. At the bottom layer, where I show you the disks, those are basically not disks, but really they indicate they represent the data nodes, and clearly the data nodes as several disks. And so you think of your bottom layer as common storage, and then you have multiple namespaces on the top, and the storage for each of the namespaces is stored on all the data nodes. So we don't partition the data nodes. So this is not like independent clusters. So you can think of each namespace has its own pool of blocks, and those pool of blocks are stored across all the data nodes. And you can think of a pool a little bit like a LUN in a sense system, okay? And so, it'll help you basically have multiple name nodes volumes, but also to do foreign namespaces, as I mentioned in my previous talk, like a temp file system or a block key value block store file system, things like that, okay? And you can kind of unify these namespaces if you like, okay? And so the question that comes up, hey, I have a lot of volumes. What do I do with them? So federation lets you do multiple volumes. Don't you need a single global namespace? And the thing is that, yes, there are times when you need it, and the times when we have tenants that actually want their independent namespace. So for example, we have a colleague who's got a startup that's doing Hadoop as a service, and in fact, for each of the tenants, he's giving them a separate independent namespace. So in fact, it's like chroot, okay? You cannot see the other guy's namespace, okay? But yeah, the cases where you do want a global namespace, and basically we do that by creating some sort of a shared namespace. A global namespace is a way to do that. And in Hadoop 2, we offer what we call the view file system, and that is basically a client-side mount table, and you can mount it and do this. So it does mean that you still have to manage the volume. So for example, it's not like transparent growth, but it is actually a very practical thing that a lot of operators are very, very used to doing, okay? And so that works really well. And the good thing about the client-side mount table is it is actually on the client-side implementation, and therefore there's no single point of failure across these volume mounts. Okay, so this is the kind of approach we see when you do want to have a single global namespace. You could do that with mount tables. Okay, so the next topic, which has been the one that get talked about a lot in Hadoop, and then I'm going to talk about high availability. So HA for HDFS, Hadoop 1 series, for example, our own distro from my company, Hortonworks, does have HA. It uses a traditional HA failover mechanism, and it uses shared storage. And if you had, let's say, 100 to 300 nodes, the failover times are 3 to 4 minutes, okay? And we have extended that work with something called full stack HA. I will talk that about a little bit later. What big change that is coming in Hadoop 2 is that we use failover using our own built-in Hadoop built-in failover controller, which means you don't have to use something like Linux HA or vSphere. So it kind of comes built in. And the other restriction that we take over, that we remove, is shared storage. So you don't need shared storage, and we use something called the Quorum Journal Manager. And in this kind of a framework, the failover times are about 30 to 120 seconds less because the standby name node is hot, okay? And so that's the main difference between the two systems. One is hot and one is not hot, okay? But the actual failover mechanism fail time still has to occur, okay? And again, this work has been extended for full stack HAs. I will explain in the next slide, okay? So what does full stack HA mean? Basically, what it means is just by focusing on the name node and saying, let's make the name node highly available, doesn't mean you've made your whole system highly available, okay? So what it means is that you need to focus on other parts of the stack, and you need to see how the other parts of the stack behave when the name node is down or the name node is failing over. Yes, the times when the name node will fail over in 30 seconds. The times when it'll take normally a minute or two, okay? But you might get situations maybe once every 3 years where there is actually a split brain. Very rare, but it can occur in any kind of high availability system. How does the system behave? Or the operator decides actually to shut down, and he would like just the rest of the system to just pause. And that's kind of what full stack HA is about. It is saying, how do you deal with this code dependency? So for example, here what I've shown is a Hadoop cluster running a bunch of jobs on slave nodes. That's the kind of top box. At the bottom, I have a name node, a job tracker, and some other things, okay? And I might even have some apps running outside, as I show on the left-hand side, outside of the Hadoop cluster that are accessing, let's say, HDFS, okay? At some point, what might happen is the name node dies, and it's going to fail over. It will take anywhere from 30 seconds to 2 minutes or what to fail over, okay? In that situation, what happens to the rest of the system? Okay, so what happened is, because what we've done in the client side, the clients are constantly now retrying, pausing, and retrying, pausing, and retrying. Okay, and so what happens is the applications don't die, but they pause and retry. And interesting things happened actually for the job tracker, and this also applies to the resource manager / application master, because the job tracker in Hadoop is actually very smart. So it kind of says, I've been running jobs, and if jobs are failing constantly or not making progress, it says maybe something is wrong with the node or something is wrong with the job itself or with the task. And so it starts bringing in its own recovery mechanism. And really, in this situation, you don't want it to do that, because the chances are that if it's waiting and retrying and not making progress, it might be because the name node is failing over. And so we have also taken that into account in the job tracker. We've changed the code so that kind of codependency situation is accounted for. And we have done this for Uzi, and tested with Uzi, HBase. There were some corner issues that HBase ran into. We fixed that. And also on, for example, the Hive H catalog, okay? So kind of, and so that's kind of what full stack HA means, that all the codependencies are taken care of. Either they pose, retry, and don't fail, okay, while the failover time is happening. And even if failover is fast, you might argue, well, if failover is fast, you don't have to worry about this problem. But anybody who's done real systems know that every once in a while, you do get times that are longer than what happens, or you get a quirky thing that happens, and so this handles that. And the beauty about this is the operator is saying, let's say the operator says, I'm not running HA. I just want to shut down the name node. He does that. The rest of the system just kind of pauses and waits, okay, if you are just doing a bounce or whatever. So it's also got uses in the non-HA automatic failover case, okay? And so now when the name node fails over, the system continues to run correctly, okay? So quickly, it's HA in Hadoop 2 supports manual and automatic failover, uses the failover controller, and there's no shared storage dependency because of the quorum journal manager that you run on as daemons on typically up to on 3 nodes, typically on the master nodes. Okay, and this is, by the way, has been available in the Apache releases 2.03 alpha. It's been available since then. That's when for example, the journal manager changes were merged in. Okay, and this is what the HA stuff looks like. What I've shown over here is an active name node and a standby name node. And then the blue little things are the failover controller. What they're doing, they're constantly monitoring it. And they may be sending commands saying do an LS operation, things like that, periodically doing a monitoring of the health. They can also be monitoring the hardware, the GC usage, things like that, okay? And they're also kind of in a leader election thing with Zookeeper. And Zookeeper has, in this particular case, elected the left-hand guy to be active. And so he's actually marked that guy as active. And at some point, if the left-hand name node fails, the leader election will happen. And the right-hand side will be told that, I guess that's, yeah, your right-hand side also. The standby side will be told that you are active. And the failover control will send a command to the name node saying, can you please move from standby mode or standby state to active state, okay? Now, one of the things I mentioned was that the name node is hot. What does that mean? What that means is that the standby name node is reading the journal information from the journal nodes. So it's constantly, every time you do an update on the left-hand side, it gets written to a shared journal system. It reads it from, it's actually always up to speed. So when it gets to start up, he doesn't have to say, let me go read what all the transactions that have occurred in the last few minutes. He's constantly, he might just be a few seconds behind. Second thing, the data nodes are sending block reports to both the name nodes. Okay, so there isn't even this time of block record recovery. It turns out actually when you're at around 300 to around, let's say I did a test on a Hadoop cluster with about 100 nodes, 1 petabyte, and about 20 million blocks. I had, for example, even though I didn't have hot, the failover time was about 90 to about 100 seconds. So on a small cluster, even in Hadoop 1, in spite of not being hot, we were actually able to do a 90-second resync at that time. Here, that time goes away. So your failover time goes down by about 100 seconds on a 500-node cluster, and even more on a larger cluster. Okay, so that's kind of what I mean by hot. So this is a pretty nice way to this addresses one of the issues that people often talk about, single point of failure. Okay. The other big kind of enterprise feature is snapshots. You can take snapshots of the entire namespace or of subdirectories. And these are managed by an admin, so the admin can give users the ability to take their own snapshots. He could say, all the users' home directories are snapshot, and the user could take his own snapshot. Or he might say, users, we never do our own backups, right? And so we might have the operator run some sort of a cron job where he actually does the backup for each of the users, maybe at a different frequency, and for data that belongs to certain projects at a different frequency. So that if somebody were to delete this accidentally, you have that. And so you no longer have to rely on this trash bin to recover accidental deletes, okay? And also it means that you can snapshot your data if you want it for a particular way to preserve it and use it for something else. Okay. Right now, we only support what we call read-only, and it's done using a copy on write mechanism. The architecture allows read-write snapshots. We haven't actually completed that work. Okay. It's a NameNode only operation. There is no data copying happening. It's only the metadata in the NameNode that's changing. There is no distributed, complicated mechanism. Data nodes, in fact, have absolutely no knowledge that a snapshot was taken. Okay, it is very efficient. It is instantaneous, and the memory use is highly optimized. Okay, so we only share the differences and the deltas that are occurring as you update your changes. Okay, and does not affect your regular HDFS operations. The other thing is that the way we have done it is very similar to what you see on NetApp systems, where you can have a path, and then there's a suffix, there's a component called .snapshot/snapshot name, and that's where the subtree of the snapshot is. So for example, for you to refer to a snapshot, you just use your regular path name and put inside it .snapshot/snapshot name. The example I've done over there below is if you lost, say, a file like an important file, you could just copy it using a regular command. Okay, so all the regular API commands appear. The only difference is when you do an ls on a directory, you will not see .snapshot there. Okay, normally it will not show it to you. Okay, so that because it's kind of a hidden file that you can use when you say it. Okay, there are a whole bunch of additional CLIs that I won't go into to allow you to create snapshots, where to create snapshots, etc. These are a whole bunch of admin commands and commands for you to see what are the diffs between snapshots. So for example, that is something, the diff is what we're going to be using to enhance this CP to only copy changes that have occurred. Okay. So this is a pretty exciting feature that we worked on for a while at Hortonworks, and we're pretty excited to bring that into Hadoop 2. Moving on to some other changes, a bunch of very, very significant performance improvements. CRC, for example, takes 3x less CPU on the read path. There are a whole bunch of improvements in the read path for fewer memory copies. So that now the I/O in Hadoop approaches close to disk speeds, or like 90% of the disk speed. Okay. Another big improvement that we originally put in for the HBase community, which was to have a short circuit, so that if you're doing a local read, you actually read it from the file system directory rather than sending the data across the socket. And that had a particularly important performance advantage for random reads, because that's one area where Hadoop code wasn't well optimized. So that was originally made available for HBase. And there's been now a generalization to use Unix socket domains. In fact, now any of your applications running, if you enable this feature, even your map task could read the data locally in a secure way from the local file system. So that's another big improvement that has been there. There have been I/O performance improvements by using POSIX fadvise, because Hadoop processes so much data that typically the cache in the buffer cache in the operating system doesn't work well, in the sense that Hadoop will wipe out whatever caching notions you may have. And so we realized that it's not going to work, and so in a sense tell the system to that, by the way, you can throw this stuff out of the cache. Okay, and so that it works even better. Okay. There have been improvements in libHDFS, which is kind of the C library for zero copy reads. And overall, I/O is 2.5 to 5 times faster, depending upon what kind of benchmark you're doing, especially for random I/O, it's incredibly faster. What also I want to kind of point out is that a good majority of these changes, I/O performance changes, actually has been ported back to release 1. So for example, if you are to use the Hortonworks 1.2 or 1.1 or 1.3 release, you'll be able to get many or most of these I/O performance improvements. Okay. Other features, as I mentioned, the new append-pipeline. In fact, that was a thing that was done earlier in 2009, I believe. We finished it 8 or 9. There is wire protocol compatibility. So now all the wire protocols, RPC layer, etc., uses protobuf and are going to be compatible going forward. So not just compatibility in the dot releases or bug releases, but across even the major releases is what we are planning to do. And this feature is very critical for rolling upgrades, so that you can now do rolling upgrades of your, you don't need to go and convert your entire cluster from, say, release X to release Y. You will be able to do rolling upgrade of your data nodes and slave nodes, okay? And this has happened both for MapReduce and for HDFS. There's some improvements for other projects like stale node that we've done for HBase, so it does, HBase can repair faster. Block placement enhancements so that it works much better on virtual machines and cloud topologies, so that the system knows that these two nodes that are supposed to be separate are actually residing on the same physical box, so you don't get co-failures occurring, say, in a cloud environment or a virtual machine environment. NFS is now available. We also backported that to Hadoop 1. And in fact, a larger ecosystem for the platform. Hadoop is now has native support on Windows in a first-class way. So overall, you see, storage fault tolerance has always been true in Hadoop from day one. This was, in fact, the biggest focus that my team had when we were at Yahoo. High availability, which wasn't there for a while, is now there. Okay, standard interfaces you can access via Web HDFS, a REST protocol. Fuse is supported. NFS is now supported, and there are a bunch of libraries that go with that. As I mentioned, wire compatibility, rolling upgrades, snapshots, another enterprise feature, and disaster recovery. In fact, disaster recovery using DistCP has been there from 2007. Okay, this is something that has not been well publicized, and we're going to actually, as part of the Apache Ambari, we're going to start providing automated management for doing disaster recovery across clusters, but there's a tool called DistTP that is extremely powerful for doing that. Now I'm going to talk a little bit about futures beyond 2.0. What are some of the things that we are thinking of? Kind of in short term, what we are looking at is really what we call heterogeneous storage. And the main motivation factor there is things like SSDs. Okay, so Hadoop, as many of you know, deals with JBODs, and it treats all the JBODs on the box as being the same kind of disk. And so at the name node level, as it's allocating, it actually has no clue of any of the special properties. Okay, so even if you were to put in a SSD, all you would notice is that your system runs faster. Now, if you could afford to make your entire cluster SSDs, which is very expensive, then you could get the advantage of SSDs. But typically, people want to put maybe one SSD on all the nodes or one SSD on a majority of the nodes. And then you want your applications in a smart way to utilize the SSDs where it really matters. Okay? And so that's what we have done. We have actually put in the hook so that now, when we identify a block, okay, so in Hadoop, at the data node, there's something called a block, which is, it's not like a sector. It's typically, megabytes of data. And that block is now identified not just with the node, but it's actually identified with the particular storage unit. And then we can add to it the storage unit's properties. So this will let us now do things like tiered storage. It will let us do things like HBase could say, you know what? I want you to put one replica of this file on an SSD. And that would make a huge difference, not for the writes, because you still have 3 replicas. It would go at the speed of the slowest one, which is the spinning disk. But when HBase has a miss on its cache, it's reading, and it'll be reading from a local disk that's an SSD. Okay? Or when it's doing a failover, it could be reading from the SSD. So those are the kind of things where we see, or somebody might say, I want to build an index, I want to put the index on an SSD. Okay? So there are a lot of interesting things that can now happen, okay, when we are able to do that. Okay? Then there are kind of block-level APIs. As I mentioned, we have generalized the block storage, and we want to start offering additional APIs over there, so you could build, let's say, a key value store like S3 directly on the block storage, as I mentioned. A lot of work in better block placement policy. So, for example, you can do co-placement of files together, so that, for example, there's a very good use case in HBase that when it does do a failover, it wants to recover in another node. It would be nice if all its files were, the second block was co-located, so it can do a much better, faster recovery. There are many, many examples of that. The other big one that we want to do is use RAM for 2 things. One is caching data that is hot, and also for intermediate query data. And this has now become very practical, where RAM prices are becoming reasonable, where you could say, I'm going to have a box with half a terabyte on each of them, and you could say, I'm going to reserve 100 terabytes actually for my, quote, RAM disk, and you multiply that by the number of nodes in your cluster. This could, in a way, give you really, really very fast queries. And so we want to use it for data that is common and automatically for intermediate data. Okay, and so that's something that we want to build into the kind of into the HDFS layer and put hooks into the compute layer, into Yarn and Tez. Okay, like I mentioned, longer term objects, key value stores, and APIs for that. The other kind of area is really kind of a generalization of the NameNode, and I'm kind of using the term name server to kind of distinguish. And really what I want to think of is a name server now is a container for hundreds of namespaces. So you could have a set of volumes per user, per tenant, per data feed, okay? And your management policies would be based on that. And then you could choose a mount table to mount them, if you like, or keep them separate because it's a separate CH root. And then you can easily move your namespace from one place to another. For balancing reasons, with this, we could easily support N plus K failover, because one of the other things we want to kind of do along with this, okay, is to simply store the working set of namespace in memory, so that you can now, one of the things about Hadoop is it stores the entire namespace in memory, which right now limits on a let's say 100 gig name node to around 500 million files. That limitation will go away, because in Hadoop, a small percentage of your files are actually hot. Okay, and so that's the thing we want to solve. And as I mentioned, I actually have an intern from CMU, in fact, Garth Gibson, student who's actually working on this right now. And so we're hoping, as soon as the prototype is done, we get some interesting numbers to start getting in this. And so really, you'll be able to scale. With this, I hope you'll be able to scale a single name node to 200 million names. And you could put this in a single volume or multiple volumes. But the general idea is that the number of name servers then will be equal to the sum of the working set. So if you have a finding that things are not fitting in memory and you have much more hotter data than would fit on a single name node, you allocate more, and so you expand your working set for the namespace and also the name node throughput that you want. Okay, and so that's kind of the generality we want for going forward. Okay, as I mentioned, a higher scalability with only the working set in memory, and we really want to move the block storage management, which is now a library, for example, in the name node, move it to the data nodes, okay? So that the data nodes manage that. And also kind of move the notion of a block to a mega block, so that you can have a lot of tiny objects inside a block, okay? There was actually a project at Yahoo called Walnut that actually did this, okay? On HA, as I mentioned, we're full stack HA, but we want to expand it to and validate it for a whole bunch of other dependent services. We want to support multiple standby nodes, including N plus K failover. Use the standby for reads. Right now, the standby is a pure failover node, but actually support it for reads. So that'll actually expand the I/O throughput that you could get. Right now we have these quorum journal nodes, and what I really like to do is to move that storage and the journal straight into the HDFS data nodes, okay, and not require this special daemon. So kind of getting to the end, looking at some of the myths, misinformation, and some of the areas we made improvements. People used to say, Hadoop is not reliable. This was never true. HDFS is not reliable. This was never true. Okay, right from early on, this was the most important thing we ever worked on, worried on at Yahoo. People used to say, in fact, one of our competitors They spin a lot of mistruths about it. They said, oh, by the way, when the name node dies, all state is lost. It was never true. It was never true even in Hadoop 0.2, 0.02 version in 2006, okay? Does not support disaster recovery. We had DistCP, and this was used at Yahoo in Hadoop 0.15 version. This was in 2007, for example, was used. Hadoop was always easy to operate for people who are good at it. So like I said, one operator for 2,000 to 3,000 nodes for a long time at Yahoo. And there's been work to now make it easier to use for people who are new to Hadoop in terms of better things in terms of the system in how it is configured, and also better things in tools like Ambari open source, which is a manager for Hadoop. Performance improvements, always ongoing. I don't believe we will ever stop doing that. Okay, we'll always focus on different areas, but major improvements in both the 1.2, 1.3, and in the 2.x families, okay? So the whole bunch of improvements that have come, and this is going to be a constant area of improvement all the time. NameNode is single point of failure. As I mentioned, we have HA that's been done. The shared NFS for HA, again, that problem has been solved. Does not have a point-in-time recovery snapshot, solve this. One of the things I didn't mention is protocols like NFS. So right now we support NFS v3. Very soon we'll be doing NFS v4, which is not just a protocol change, but will have very interesting improvements in how fast NFS can access HDFS, okay? It'll have the same parallel access that you see in PNFS when you go to NFS v4. So your NFS access will also be significantly better. So anyway, this was my last slide. Thank you very much. So I'm open for questions.
Are the snapshots atomic? And
yes.
In the context of like HBase, if I take a snapshot underneath, what is the recovery mechanism and how does it work?
Okay. So if you were looking at it from a snapshot point of view, it is atomic. There's a lock that happens and happens. Now, the thing that happens in something like HBase is that if you have an application like HBase and you are making multiple changes to multiple set of files, a snapshot that an operator takes is consistent from that point of time, but it may not be exactly what HBase wants, because HBase wants application-level consistency at HBase level. Okay? So right now, HBase has something called an HBase snapshot that they do using what they call soft links. And that is going to migrate over, we believe, to use HDFS snapshots, where they do a certain QoS, do a snapshot so that you get a client-level consistency at the same time. Okay? So just because you have atomic snapshot at the lower level doesn't mean the layer above, because it's doing multiple operations in parallel. So it's the same problem you had if you were implementing HBase on a NetApp filer. Okay, so we're going to work with them so that the HBase snapshot uses HDFS snapshot. But other questions?
Another question about snapshots.
Yeah.
When we take snapshots, there is a delta space which is consumed to prevent the changes.
Correct.
Is that at file level or HDFS block level?
No, it is just at the namespace file level. There is no duplication of any data whatsoever. In fact, the data nodes that store the data don't even have a clue that a snapshot got taken.
Got it. Thank you.
Okay, so it's very fast, very efficient.
Maybe this is a question for the Yarn staff, but in the Hadoop stack, the next MapReduce component like resource manager, still it is a single point of failure. Would you care to answer?
Okay. So the way Yarn has been designed is actually now it is a much more distributed system. So first thing about Yarn is that when certain components fail, the whole system doesn't fail. Okay, so it has a built-in notion that, for example, if the resource manager fails, other things can continue to run. All you cannot do is start new jobs or submit new jobs. Okay, so it is a distributed architecture that is much better than having a single point. Okay. Second thing is, yes, they have a recovery for the application masters, which is now per application master per job, so that's what they recover. And they also have or are working on a recovery for the resource manager. Okay, the resource manager, I do know, does not lose its state of jobs anymore, for sure. Okay, in fact, that was also fixed in Hadoop 1. The job tracker in our HTTP distribution does not lose job history. I mean, the jobs that are in the queue. But yes, it is. We are looking at HA for not just HDFS, for each of the components, and we're also looking at the interdependencies on how failures occur. But yes, absolutely.
A quick question on the block level semantics you're talking about. So can you kind of expand a little more on, does it have any dependency on the name node?
No.
Exactly.
So the block layer is completely independent. In fact, it always was independent. So architecturally in Hadoop, in HDFS, the block layer and the namespace layer were actually architecturally separate. But in the code, there were a whole bunch of funny dependencies, one. Second one is the block layer had no notion of having multiple clients. Okay, it said there's only one client. It is whatever the master name node is. That two things got changed. One is that the separation from a code basis has improved, and the data nodes now say each of my blocks belong to a pool, like a LUN. And the LUN has an owner. Whoever that owner is manages what to do with it. So now there are multiple name nodes. You could run another block store, another higher level system like, say, key value store, or you could run HBase directly. So all those things are now possible. The two layers are, the bottom layer does not know about the top layer.
And so who's responsible now for the replication and data recovery?
Good. So question. So what we have done is we've taken the code that was doing the replication. It's still in the name node, but it has now been factored out into a separate package. Our goal is to make it a library. Okay? And then when I mentioned in my talk that I want to move the block management out to the data nodes, what I want to do is to take that replication stuff automatically happen. So even if you were to shut down the name node, the data nodes will say, I know the replication factor of this. They might have a leader election master, haven't figured out the details, but it'll happen. In which case, for you to write a new name node or a new service on the top that uses it, you don't have to worry about the replication. You don't even have to use the library that we have. And that's how easy we want to make it. OK, good question.
I have a question on the snapshot. Are there any redundancy for the snapshots? Do you do replications for the snapshot?
So the snapshot is a metadata game that is played. Okay. So what is happening is that you have some directories, and you take a snapshot. It remembers that time, and then as you change it, it keeps the original view. So that view is kept in the name node. Now the name node naturally takes its metadata, and as it writes its metadata, it writes in multiple storage systems. And you can configure a name node to say that its metadata is replicated. Okay? That means its journal is replicated, its image is replicated. The replication of the data is unchanged. So if you had a replication factor 3, we do not change it from 3 to 6 or anything like that. So the data nodes continue the same level of replication. The reliability of the snapshot is now based on the same reliability as the name node, and you need to make sure that your name node has multiple storage units that are replicating it either because you're running it as RAID, or you're running it the Quorum Journal Manager because it's now 3 journal nodes that are doing it, whatever schemes or various is, but it's reliable. OK, let me answer, then come back to you. Go ahead.
This question is regarding the individual storage units on data node. So you mentioned that, you can specify certain blocks to be stored on SSDs, in future. So is there a possibility that, you can uniformly distribute your blocks on multiple disks on a data node? Like, say, for example, if you have 12 disks, then you can uniformly distribute them? So
today, HDFS does actually uniformly distribute the data on the spindles. And it also uniformly distributes the data across all the data nodes. Okay? And then if it sees that one of them is getting full, it gives it a lower weight. But today, it automatically does that. And that's got nothing to do with the storage identity. That we are still, if you, for example, specify, I want to write this is what the plan is, okay? That when you write, it'll still continue to say, I will distribute it. Now, if you say, I want it on a disk of a special property, and there are multiple disks of those properties, okay, let's say 3 SSDs and 3 spindles, then it'll distribute it on the 3 spindles that have SSD, SSD don't have spindles, but the spindle one or the other one. So we will continue those properties.
Yeah, and can an administrator specify a policy depending upon the capacity of the disk that put 2 blocks on the first one and then third one on the second one or something, like if the storage capacity is like twice or something?
That one is trickier. You need to be very careful about this, because what can happen is you can have spindles that become very hot. Okay, so we have to kind of look at a way to make this happen automatically. In fact, people also say, can I make my data, for example, when you add brand new data nodes, they say, why isn't the new data nodes automatically getting filled up with my new data? Obvious, right? That's where the space is. You're writing new data. Why do I have to run a balancer to copy the data there? Is HDFS stupid to not just write it there? No, we were not that dumb. It is because if you did that, those nodes would become hot. They would become so hot. So we have to unify so that the Hadoop model of move computation to data has many choices, okay? And your stuff happens. The same issue applies at the disk level. If you want to blindly go and say, go and put stuff on the most empty spindles, those spindles will become hot. So we have to do it in a more intelligent way. There isn't an intelligent way to, I mean, it's pretty, we have to do something smarter there when disks are unbalanced, what do you call it? Unbalanced capacity to start with, or there's a thing about what happens when I remove a disk and just replace one disk with a brand new one because it was flaky. So that's something that we do have to solve. Okay? Somebody had a question here?
Yeah, question about the NFS support and DFS fuse. Are they both same or there is
No, different. So NFS fuse is basically a daemon. So Linux has a fuse module, which basically lets you implement a file system in user land. And that could be a file system locally or remotely. And that has always been there in Hadoop for quite a few years. NFS is now saying that Hadoop has daemons that will now obey the NFS protocol. So you could then NFS mount it onto your system and then do a CPA to B, and if B was your mount point for your thing, it'll copy it there. Today, in the current version, because it is doing NFS v3, okay, there are daemons that you have to deploy. Okay? When we do NFS v4, in fact, NFS v4 was easier for us to, but we did 3 because there are more customers that need it right now. In v4, we would actually build this into each of the data nodes and into the name node, so the name node will redirect you to the place where the data is local. So in fact, it'll have the same parallel access capability that Web HDFS does and that HDFS does, okay, with a single mount point. Right now, with the daemons, you'll have to project multiple mount points going through a daemon, okay? Still very usable right now, and so it's a significant thing for a lot of our customers, and it's going to get even better.
Ladies and gentlemen, please join me in thanking Sanjay for his presentation.
Okay, thank you very much.